So the 60 over 180, we're just reducing it. We're dividing out common denominators, or common factors. Now we could factor it all out and just cross off common factors if we wanted to. But if we look at that, what do we notice that both of those can be divided by? 3 would work. 60 divided by 3 is 20. 180 divided by 3 is 60. Anything else they can both be divided by? 10, because they have a 0. So that's 2 over 6. And finally, 2. So you get 1/3. You could have divided by 30 right away if you'd seen it, but you don't have to. The other option, as I said, is to do prime factoring. 60 is 2 times 2. Is it times? 3 times 5, that's what I thought. 180 is 2 times 2 times 3 times 3 times 5. And we just cancel out. There's a 2, a 2, a 3, and a 5. We're left, everything on top cancels out, so that's 1, and we're left with a 3 on bottom. So it's 1/3. Well, these other ones kind of have to do that way. We don't necessarily have to factor them out, but we have to use that concept. So for the second one here, we're going to do the shortcut. I'm going to take out the number first. 20 over 30, what can I do to reduce that? Both of those can divide by 10, gives me 2 over 3. That is as far as I can reduce it. So in my answer, I know there's going to be a 2 in the numerator and a 3 in the denominator. What do I do with the variables then? For x, where does it go? It'll be on top, because the larger power is x to the 5th, and that's on top. So x goes on top. What power is it going to have in my answer? 2 squared. 5 minus 3 is 2, so x to the 2nd. Where is y going to be in the result? On bottom, because y to the 3rd is larger. 3 is bigger than 2. What's its power going to be? 1 or just y. 3 minus 2 is 1, so y to the 1 or just y. Any questions on that one? Okay. Number 3 then. We go to reduce the number. We do have to be very careful here. We have that 12 over 8. Both of those can be divided by 4. Gives me 3 over 2. It is really, really tempting to try to split that into 1 and 1/2. We can't do that. Why can't we do that? Because we have the variables. We don't know what value those variables have, so we don't know if this is an improper fraction or not. So we've got the 3 over 2. What do we do with the a's? It's on top into the power of 4. Good, because a to the 5th is the bigger. Of course, that's a to the 1. 5 is bigger than 1, so it goes on top. 5 minus 1 is 4. How about b? Bottom and just b, right? The bigger power is the 4. That's on bottom. 4 minus 3 is 1, so it's b to the 1 or just b. How about c? Bottom and squared, 2. Think of that as 1, so 3 is the bigger power. It's on bottom. 3 minus 1 is 2. So we get 3a to the 4th over 2bc squared. Any questions there? Okay, well then, let's go down to these bottom two for simplify. Seven a to the 5th over 5b to the 7th, and this is all to the 3rd power. First thing we should look for, is there anything we can reduce inside that parentheses? The answer is no. We can't. The 7 and 5 can't be reduced as a fraction. and the a to the 5th, b to the 7th, there's nothing that can divide out or combine it all there. So then what we're going to do is we're going to split this down. So it's the numerator to the 3rd power, so 7a to the 5th to the 3rd power, and then the denominator to the 3rd power. So 7a to the 5th to the 3rd power. Remember, we do each piece separately. What is 7 to the 3rd power? 343, good. A to the 5th to the 3rd power is careful. When you have a power of a power like this, the exponents, the powers are multiplied. 5 times 3 is 15. Now on bottom, 5b to the 7th to the 3rd power. We take the count first. 5 to the 3rd power is 125. We do have to do 5 times 5 times 5 for the count. It's just the power gets multiplied. So it's b to the 21st. Good. So there it is, 343, a to the 15th over 125, b to the 21st. Over here in number 5, our last one, we should reduce that fraction before we do the power. So I'm going to start off with the 8 over 6. Is there anything I can reduce there? We can divide by 2, which would give me 4 over 3. Anything that can be done with the x's? Yes, x to the x on top or bottom, first of all. Top and to the power of 3. 5 minus 2 is 3. The y's? Just a y on the bottom. Perfect. 2 and 1, 2 is bigger, so it's on the bottom. 2 minus 1 is just 1. So y to the 1 or just y. Now this whole thing still is to that power of 5. And of course we know we can do, the top to the power of 5 and then the bottom to the power of 5. So on top, we're just going to do each piece. 4 to the power of 5 is 1,024. X to the 3rd to the power of 5. X to the 15th. Good. 3 to the power of 5. 243. Very good. And then y to the power of 5 is just y to the 5th. You can think of that as 1 times 5 is 5 if you want to. I realize those are not the most enjoyable problems you've done this year. We are going to come back to those algebraic fractions. Once we do more our operations with fractions and working with fractions more, we are going to bring in those algebraic fractions for working operations with them as well. But for now, we're going to set them aside. And tonight, we're going to work mostly with numbers. We're going to talk about ratios. What a ratio is simply a comparison between numbers. For example, let's do a ratio here of students in New Richmond and students in Rice Lake. Right now we have 1, 2, 3, 4, 5, 6, 7 students in New Richmond. We have 5 in Rice Lake. I shouldn't say that too loud. This is a low batting average tonight. That's a 7 to 5 ratio. And I can write it exactly like that as a fraction. I could write it with a colon, 7 colon 5. Or I can even write it with the word 7 to 5 in this case. This wording here is only can be used in specific cases. And we'll talk about that in a little bit. Other comparisons we might have. We might have students that are gone tonight to students that are here tonight. Well, we have 12 students here. We have 10 students that are gone total. I usually write my ratios as a fraction because there are a lot of things I can do with my ratios that are similar to what I can do with a fraction. First of all, 10 over 12, both 10 and 12 can be divided by 2. So it's a little bit simpler to say that it's a 5 to 6 ratio rather than saying a 10 to 12 ratio. Now, there are some things that are a little bit different about fractions that I can do with fractions that I can't do with ratios. For example, if I look at the tables in this room, I'm a little bit different from the tables you have in New Richmond. The tables here are 18 inches wide and 72 inches long. So let's do a length to width ratio. Well, the length here is 72 inches. The width is 18 inches. First thing that can happen is the inches can cancel out. Well, both 72 and 18, you may not see the 18 at first, but you can see they can both be divided by 2 and 3. They can both be divided by 18. 72 divided by 18 is 4. 18 divided by 18 is 1. Now, if this were a simple fraction, we'd just write that as 4. 4 over 1 is 4. But it's not. It is a ratio. And a ratio is a comparison between two numbers. So we have to always have those two numbers there. So we would have to leave this as 4 to 1 as a ratio. Now, something you'll notice here, by the way, this is a special kind of ratio. This is called a unit ratio because the denominator, the bottom of the fraction, the second number, is a 1. We're comparing something to 1. We're comparing it to a single unit. Anyway, you may have noticed in all the ratios I've created so far, we're comparing two things that are alike. Students to students. Here again, students to students. Down here it was inches to inches. Now obviously there has to be something different about them, or why would we put them in two separate categories? Like New Richmond to Rice Lake, but it's still New Richmond students to Rice Lake students. Or gone to here, but still students that are absent to students that are here. They still have a common label. Length to width, it's inches of length and inches of width, but it's still both inches. If I had 2 feet compared to 18 inches, that is not a ratio because those are two different units. Now I can turn that into a ratio by converting 2 feet into 24 inches. So now it's 24 inches to 18 inches, and it is a ratio. The units are the same. So the inches can cancel out. And of course I can reduce that. 24 and 18 can both divide by 6. 24 divided by 6 is 4. 18 divided by 6 is 3. It's a 4 to 3 ratio. Now here's another difference between our common fractions and ratios. In a common fraction, I'd be really tempted to reduce that to 1 1/3, and that would be appropriate. For a ratio, it would not be. We cannot turn it into a mixed number because a ratio is a comparison between two numbers. Similar to our algebraic fractions that way, we can't make it into mixed numbers. Now, I had said something up here about the wording, the 7 to 5. There are two types of ratios. There are ratios that compare separate groups. Helps if I put my R in there. So separate groups are one's not included in the other. Like our New Richmond students compared to Rice Lake students, those were separate groups. There are also ratios that do a part out of a whole. This would be asking, well, how many New Richmond students do I have out of the whole class tonight? Well, there's 7 students in New Richmond out of 12 total students. Up here, though, it was 7 students in New Richmond compared to 5 in Rice Lake. So this was 7 to 5. They're completely separate things. They're not part of the other. This is 7 out of 12. So what that's implying is the 7 that we have listed here is also part of the 12. Which will bring us to some interesting things we can do with those, by the way. Come on now. If it's a 7 out of 12, well then of course there's other ratios that are implied there. You got the 7 out of 12 ratio or 7 to 12 ratio. That is the New Richmond to total ratio. If we know that there's only one other group, the Rice Lake group, from that we could get the Rice Lake to total ratio. Because if 7 are from New Richmond out of 12, that leaves how many? 12 minus 7, 5 out of 12 are from Rice Lake. A good example of this is in medicine, it's called a dilution. A dilution is your parts of medication out of your parts of total solution. So a 1 in 5 dilution is 1 part medication. Come on. To 5 parts total solution. Now, we're not going to get real deep into the medical side of this, but in a dilution, you have the medication and then the rest of it is sterile water that is mixed with it. So if 1 part out, and this is 1 part out of 5 is medication, we can come up with the ratio of water to total solution, because the total solution is still 5 parts. How many of those parts are water? 4. 1 part's medication, 5 minus 1 leaves us with 4 parts water. Now we could also do the medication to water ratio. Of course, there's 1 part medication to 4 parts water. That one's a little bit harder to pull out of there, but you're just taking the individual pieces. Of course, this one would be 1 out of 5. This would be 4 out of 5. This is 1 2, 4, because one is not included within the other. So I made a big deal about these ratios. All of them have the same units. You know, if this is medication is measured in milliliters, the total solution is measured in milliliters. Up above, we had to have inches compared to inches. Well, what if we were comparing two things that do not have the same units or do not have the same label? Let's say you go on a road trip and you travel 365 miles in 7 hours. There is no way we can convert miles into hours or hours into miles. It can't be done here. So this cannot be a rate or a ratio. This is what we refer to as a rate. So that is the first difference between a ratio and a rate. A ratio compares two things with the same label. A rate compares two things with different labels. The second thing between a ratio and a rate, in my ratios, I had no problem leaving it as 1 to 5 or 5 to 12. I did mention that there is a unit rate where I have it as 4 to 1, but we didn't have to convert it to that. Or unit ratio, I should say, is 4 to 1. Ratios, we usually just reduce them and leave them where they're at. Rates are almost always reduced to a unit rate. A unit rate means the denominator equals 1. So we take the numerical value in the denominator, which for this is a 7, and we're going to divide by 7. 7 hours divided by 7 is 1 hour. Now, of course, if we divide the bottom of a fraction by 7, we have to divide the top by 7. 365 divided by 7 is, what is that? 52.142857143 approximately miles. Don't worry, it's not contagious. I've mentioned before, math is about patterns. Once you see the patterns, the calculations are simple. That's just one of the patterns there that you start to recognize. So it's a unit rate now. The denominator is 1 unit, 1 hour. Now, many times once we have it in a unit rate, we'll rewrite it. Now, I'm going to round this to the nearest hundredth. So 52.14, first of all. And we disguise that appearance of a fraction. We take it out of the numbers and we disguise it within the units. So we might write it as miles per hour like that. In fact, there are many times where we disguise that appearance of the fraction even more. We eliminate it by the way we write the label on there. For example, let's say on that trip, you got 24 mpg. What does mpg stand for? Miles per gallon. Whenever you see 24 mpg, you need to think this, 24 miles over 1 gallon. Because that is the form you're going to need it in to do any calculations with it. Okay, well, we've seen a few examples of ratios. Let's talk about a few more examples of ratios here. Remember, ratios are all things that have the same label or the same unit. One ratio, if you look at mechanics, mechanical design, even a little bit in architecture and stuff like that, one that comes up. Now you're going to have to use your imagination here because I'm drawing pictures. And anybody who's ever seen me draw pictures knows when I draw pictures, you have to use your imagination. No, that's not the sun, by the way. Anybody have any guess? Gears, there we go. This is a gear ratio. Yes. Gear ratios are the number of teeth in the driven gear. Come on now. Compared to the number of teeth in the driving gear. Well, how many teeth does this big gear have? I'll do you a favor. I'll mark one of them purple so you got a place to start counting at. 15, okay. How about the little gear? 9, okay. We'll settle on 9. Well, how do we know which one's the driven and which one's the driving? Well, at this point, we don't. So let's go back to my artwork. Pretend that looks like a little electric motor. Now, if that big gear, that 15-tooth gear is hooked to a motor, if I separate them, which one stops turning? The little one, the 9-tooth, will stop turning. That is the driven gear. It's being forced to turn by the other gear. The 15-tooth gear then is the driving gear. It is driving the other gear. It's the one that's hooked to power. Now, of course, that ratio can be reduced by what? 3, good. So I get 3 to 5. So it's a 3 to 5 ratio. It's a ratio of the number of teeth in the gears. It's also a ratio of the speed of the gears, the number of revolutions of the gears as well. It'll also be a ratio of the powers at some point too, if we got into that. But that's not our purpose here. The reason we count teeth on the gear is what we're really comparing is the size of the gears. Now, my pictures here are pretty shabby, but for 2 gears to mesh together, the distance between teeth has to be exactly the same on both gears. If it's even slightly different, as they start turning faster and faster, eventually they're going to bind up. So counting the teeth is really nothing more than measuring the distance around the gears. So very similar to a gear ratio is a pulley ratio. Now, pulleys don't have teeth, and rather than measure the distance around the pulley, the circle, if we just measure the diameter, the ratio of the diameters is the same as the ratio of the circumference, the distance around. So let's say that this is a 10-inch diameter pulley. This is a 4-inch diameter pulley. Now, once again, it's driven over driving, so I need to show you which one has a motor hook to it. So we'll pretend that looks like a motor. So now again, if I cut the belt, which pulley stops? The 10-inch. So that one is the driven pulley. It goes on top. The 4-inch then is the driving. It goes on bottom. What can I reduce here? And cancel the inches. What else? Divide by 2. I get 5 to 2. Can I make that 2.5? No. It stays as 5 to 2. Let's do one more mechanical ratio. Wonder where that came from. If you can guess what it is, tell me. Pistons, there we go. Hey, my artwork isn't that horrible, huh? Don't go pat myself on the back quite yet. These are two pistons. This is actually a compression ratio. And a compression ratio is the expanded volume compared to the compressed volume. So the expanded volume is when the piston is at the bottom of the stroke. When the volume above it is the maximum, let's say that is 480 cubic centimeters in this cylinder. The compressed volume is when the piston's at the top of the stroke. Technically, of course, the connecting rod would be going down at that point. So it's at the top of the stroke, so it's the minimum volume above the head of the piston. So that is 60, let's call that 60 centimeters cubed. Again, those are numbers I had to give you in this case. So that would be 480 centimeters cubed over 60 centimeters cubed. Of course, the centimeters cubed cancels out. What else divides out? 10 will divide out. That gives me 48 over 6. What else? Both will divide by 6. 48 divided by 6 is 8. 6 divided by 6 is 1. So it's an 8 to 1. Now this one happened to come out evenly as 8 to 1 exactly. A compression ratio is one of the few ratios that is pretty much always reduced to a unit ratio. So even if it didn't divide out evenly, you would want to divide that one down. Let's go away from the mechanics, but let's go to construction. Let's look at a roof. Let's say we have a roof with a 24-foot span, and the height of the peak is 6 feet tall. There are actually two different ratios involved with a roof that people often confuse or often think are interchangeable. The first one is the pitch, and the pitch of the roof is the one that most people get wrong. The pitch is actually the height over the span. So for this roof, the height is the 6 feet. The span is the whole span, the 24 feet. So the feet cancel out. Both 6 and 24 can divide by 6, giving me a 1 to 4. That is a 1 to 4 or a 1/4 pitch. And that is the proper way of designating a pitch, is 1/4. Come on. Slope is actually rise over run. Rise is still going to be just this height here. We rise 6 feet. But the run is from one end to that highest point. That'll be half of the 24, only 12 feet. Now there's still a ratio because both of them are feet, but the feet cancel out. It's typical. Now I purposely chose the 24-foot span so that the bottom of this would be 12. The slope is typically stated as out of 12 because there's 12 inches in a foot, so it's really your inches of rise per 1 foot of run. So a 6/12 slope. A 6/12 slope and a 1/4 pitch mean the same thing. A lot of people will say, oh, there's a 6/12 pitch on that roof. It's not. It's a slope, not a pitch. Let's see. Other ones that are good. We talked a little bit about medicines. Let's talk about medical concentrations. It really doesn't even have to be medicine. It can be any chemical. But it can be the amount of the active ingredient to the total solution. So let's say that we have 20 milliliters of iodine in an 80 milliliter solution. So that's going to be 20 milliliters to 80 milliliters. The milliliters do cancel out. I'll give you a little shorten up this reduction. Both of them divide by 20. That's a 1-to-4 ratio, or 1 out of 4, 1 in 4 ratio. What would be the concentration then? And be careful with this. If we mix 50 milliliters of, I'm just going to put iso for isopropyl, partly because I'm not sure if I can spell isopropyl. Isopropyl alcohol with 100 milliliters of water. What is the first number of that ratio? What's my active ingredient there? "50 milliliters of alcohol." Here's you're going to have to stop and think for a second, because your first instinct is going to be wrong here. What goes on bottom? The total solution is going to be the 100 milliliters of water plus the alcohol, 150 milliliters. So first milliliters will cancel out. Both divide by 50, you get a 1-to-3 ratio. Another one that's going to be important, whether you may not realize it's going to be important to you, and when it happens, you may not even realize it's being used. But one that is important and will be important to you is something called a debt to income ratio. And what this is when you go to get a loan, there are actually two things that take part in you getting that loan. There is your credit score that you hear about. And you hear a lot about that. They make a big fuss about that. Most loans have a minimum score. If you're below that score, they won't give you a loan. It's usually, depending on the type of loan, for home mortgages, it's usually 675. They want you above that. For cars and stuff like that, there are lower scores that are minimum scores. But as long as you're above that minimum score, the credit score does not determine whether you get the loan or not. What the credit score determines is your interest rate. The higher your credit score is, the lower rate of interest they give you, because they're pretty sure you're going to end up paying them back. If you have a lower credit score, they usually charge a higher rate of interest because there's a greater chance that you may default on the loan. It's the debt to income ratio that generally determines whether you get the loan or not. And what this is they're going to take your gross income, gross pay. So let's say you work 40 hours a week times 4 weeks a month times $12 per hour. Was that $1,920 a month as income? That's your income then. Your debt is only debt payments every month. So over here, let's say you have a car Let's say your car payment is $240. Let's say you have credit card. Let's say your credit card payments. Now your credit card payments, usually you can list your minimum payments, but they want you to list a little bit above that. A lot of times they'll sit down and they'll take your balance and they'll figure out what your payment would be to pay it off in a certain number of years, like 7 or 8 years. Most of the time, your minimum payments are set to pay off your credit cards in between 20 and 25 years if you only made minimum payments. So let's say they determine that your credit card payment, your minimum credit card payment should be $180. And let's say you have a student loan. So the student loan is the one that usually gets people. But let's go easy on ourselves. Let's say your student loan's $100 a month. So the total here is $520. What is your debt to income ratio right now? Well, $520 of debt every month, $1,920 worth of income. Notice I didn't figure in groceries, gas, anything like that. These are debt payments that are paying off debts every month. They don't take into account lifestyle. Both of these numbers can be divided by 10. They can still be divided by I'll help you out. Let's go with 4. Speed it up a little bit. 52 divided by 4 is 13. 192 divided by 4 is 48. So 13 out of 48. They typically are shooting for a 1 out of 3 maximum. Using what we know of fractions, 1 out of 3 would be how much out of 48? Well, it'd be 3 times 16, so 1 times 16 would be 16/48. We're below that. So that's not a bad debt to income ratio. Let's say you want to buy a house. And the house that you're proposing to buy has let's do this. A $360 a month house payment. Now that's the house payment, not the taxes. Bless you. Not the taxes and insurance figured in, just the house payment. What you actually pay every month would probably be closer to $500, maybe a little bit more. That's just the part that goes towards the mortgage. So that's $880 now total. So when they're considering that mortgage, they would go off of that 880 just to see where it would put your ratio at. Both of those can be divided by 40, which is going to give us, was that 22 over 48? I'm going to stop there. I know it can be reduced to 11 over 24. But the reason I'm stopping there is we already figured out up here that 16 out of 48 was the highest our debt could go and still be below that 1 out of 3 ratio. 22 would put us well over that. So the bank's most likely going to look at us and say, we cannot afford that house payment until we reduce our other debt. It's time to pay off the credit cards. Ratios are pretty simple. Ratios are all around us. We talked about miles per hour. You're used to seeing that on your speedometer, but you also saw us reduce the 365 miles in 7 hours, whatever. Let's say you drive 240 miles on a tank of gas. That tank of gas turns out to be 12 gallons. Well, for rates, we tend to convert them into unit rates. So we're going to divide by the 12 on bottom. 240 divided by 12 is 20 miles. 12 gallons divided by 12 is 1 gallon. So 20 miles over 1 gallon, we'll take it into 20 miles per gallon. One that you're probably more familiar with. Let's say at your work, you're getting paid $418 in 38 hours of work. So again, we're going to reduce that down. What are we going to divide each of those by? Because it's a rate, it's just going to be the denominator, 38. So 38 hours divided by 38 is 1 hour. $418 divided by 38 is $11. That's $11 in 1 hour, or $11 per hour. Any questions? Okay, it is time for a break. It is 4:21. So let's take our break here. We'll come back at 4. Aren't they the same thing? No, because what this is saying here is that's saying z to the 5th squared means times itself. So this is z to the 5th times another z to the 5th. So you think of it as 5 plus 5 makes 10. Or you just do the 5 times 2 to get the 10. Does that make more sense at all, or are you still confused? Let's do this. I'm going to change that 2 to a different number just to make it a little more obvious. Let's say it's like that. So the 3 still has to be squared. That is, it's 3 squared and z to the 5th squared. Well, 3 squared is 3 times 3, or 9. Z to the 5th squared is z to the 5th times z to the 5th, or z to the 10th. And the shortcut is just to multiply the powers on the variables. Okay. And we will spend more time working with those variables again before we get to another test. Don't worry. Okay, so we've talked about ratios and rates. So I want to spend a little bit of time looking at some examples of ratios and rates and picking out which one is which. So for example, let's say that you look at the label of a bottle and it says, give 4 milligrams for every 100 pounds. So this is giving us this comparison, 4 milligrams over 100 pounds. First of all, is that a ratio or a rate? Careful. It's a rate. A ratio, the units have to be the same. If the units are different, it is a rate. A ratio, same units. A rate can have different units. So since this is milligrams and pounds, it has to be a rate. Now, most rates would get reduced to a unit rate. This is one where it's not going to happen that way, or we probably could. Let's do it. Let's divide out the 100. So 100 pounds divided by 100 is 1 pound. 4 milligrams divided by 100 is 0.04 milligrams. So as a unit rate, that gets listed out as 0.04 milligrams per pound, like that. Let's say I give you the example of a school. Wow. Has 17 teachers for 357 students. So I'm going to construct this ratio, 357 students over 17 teachers. Now, I purposely wrote this one out in such a way to make it a little confusing, because this is one that is a little confusing. It's a little bit gray. Is it a rate or a ratio? Well, you can make the argument either way, because you're comparing students to teachers, right? Those are different units. So you can make the argument that it's a rate because we are comparing students to teachers. If we divide out by 17, that is 21 students to one teacher. Yes. If it's a rate, you usually divide by the bottom number. Ratio, just reduce it like you would any fraction. Divide out what can divide into both numbers evenly. So that's a 21 student to one teacher rate. So 21 students to teacher. The other argument could be made that it's comparing people to people and that it's a ratio, a 21 to 1 student to teacher ratio. So like I said, I purposely made that one a little foggy, a little cloudy. Some of these cannot necessarily be specifically classified as one or the other. It's a little bit open to interpretation. How about I mix 20 milliliters of medication into a 120 milliliter solution. So I'm going to take my ratio here, or take my numbers here of 20 milliliters over 120 milliliters. Ratio or rate? This one is a ratio, comparing milliliters to milliliters. And one of the unique things about a ratio is since the units are always the same, the units are always going to disappear. Now, both of those numbers can be divided by, could be divided by 2 or 10. They can actually both be divided by 20, which is going to give me 1 to 6. Notice a ratio never has any units on it. This is 1 to 6. This is 21 to 1. Even though it says student teacher, that's telling me what the ratio is. This is 1 to 6. It would be a medication to total solution ratio. But it's still just 1 to 6. There's no units in the ratio itself. Should just have to give the 1 to 6. The unit should be listed off to the side. The unit should be given for you. So what are we going to do with these rates and ratios now that we have them? Well, let's look at that gear ratio. Let's say that we had that 5 to 3 gear ratio. And we had to maintain that 5 to 3 gear ratio in order to make the device we're using work. And we find a motor that already has a gear on it with 18 teeth. Does that motor represent, the gear on that motor represent the driving gear or the driven gear? If I if I disconnect the two gears, will the one on the motor keep spinning or stop spinning? It'll keep spinning. So it is the driving gear. I don't expect you to know the terminology. So that goes with the bottom. That's the 18 on bottom. So what we are looking for is how many teeth do we need in the other gear? To find that, we're going to set these two ratios equal to each other. We need this ratio to equal 5 to 3. If we have 18 in the driving gear, we're going to find how many we need for the driven gear. There's a couple ways we can go about that. We can treat it as fractions. 3 times what makes 18? Well, that'd be 3 times 6. So 5 times 6 makes 30. That'd be a 30 to 18 ratio. So we need 30 teeth in that other gear to maintain that 5 to 3 gear ratio. Now, if I look at what happened there, I just used equivalent fractions to change those numbers to make them equal. It's not always quite that simple. I might have a 9 and 15 ratio, and I want to figure out, well, how much is that going to be if it has to be out of 25? Well, what do I multiply 15 by to make it 25? Careful. It's actually 1 2/3, right? Well, how do I get the 1 2/3? Well, I can work backwards. To figure out what I'm actually multiplying by here, I'll work backwards. 25 divided by the 15, right? Once I have that number, I'm going to multiply the top by it. Well, what I have up here is a recipe for solving for that missing number. 9 times 25 divided by 15. Now, technically, the parentheses in there say we would have to divide first, but this is a case, since it's all multiplication and division, we can cheat our order of operations a little bit. If you look at that, 9 times 25, and then divided by the 15 over here, you can see the 9 and the 25 are on the same, they're diagonal to each other. When we look at these things, this is called a proportion. And a proportion is what we get anytime we have two fractions that are set equal to each other, whether it's two ratios or two rates. And to find a missing number in a proportion, so let's say that number, well, let me just rewrite it. So let's say we have this number up here is missing. To find that missing number, we look at the diagonals. And these proportions always have two diagonals, this way and this way. One of the diagonals will have both numbers. In this case, it's the A and the C. Those two numbers get multiplied together. The other diagonal is the one that has the missing number in it. So we take the number that's on that diagonal and we divide by it. So it's going to be A times C divided by B. Now let's go back to this one up here and actually do with numbers. So in this proportion, again, we have two fractions that are equal to each other. What two numbers are on the same diagonal? 9 and 25. We're going to multiply them. 9 times 25 is 225. Then we take the number that's on the other diagonal and we divide by it. 225 divided by 15 is 15. So 9/15 is equivalent to 15 out of 25. technically what's going on here is this. We've solved some basic equations so we can handle doing this. If this is my variable right here, I want to solve for it. Remember, we talked about getting the variable by itself on its side of the equation. What's keeping x from being by itself right now? The 25. What operation is attaching the 25 to the x? It's divided. How would we get rid of it? We would multiply by 25. Multiply the other side by 25. Well, technically on the other side, what would happen is this. This is 9/15. You'd be multiplying by 25 over 1. So what you would do, you'd multiply straight across. 9 times 25. On bottom, 15 times 1 is 15. So the result is 9 times 25 and then divided by 15. Does that make sense? So the shortcut is cross, multiply, and divide. What two numbers are on the diagonal again here? 9 and 25 are diagonal with each other. So you multiply them and divide by the third number. Well, let's look at another example of that. Let's say we have Yeah, go ahead. This is the one. This is the proportion up here. So this is where you cross multiply and divide up here. This is not a proportion anymore down here. Down here, these are multiplying, not equal. The equal sign in there, that's where you cross multiply and divide. So let's look at this one, trying to find that missing number, x. What two numbers get multiplied there? 4 and 48. So I cross multiply. 4 times 48 is 192. Then what do? We divide by the 64, which gives us 3. So x here equals 3. So 3 out of 4 is equivalent to 48 out of 64. Let's see here. So how about 5 out of 7 is equal to x over 10. How do we find x? Perfect. 5 times 10 is 50 divided by 7, which is 7.142857143 approximately. Or we might have 14 over 5 equals equivalent to 35 over x. In this problem, what two numbers are going to get multiplied? Yeah, the two numbers that are diagonal here are the 5 and 35. So 5 times 35 is 175, right? Then what? Divide by 14, which is going to give us 12.5. Does that make sense so far? Okay. These, yeah, that's good. Yeah. Okay, now that's a good question. I was kind of waiting for that one to come out, actually. My My math lab might say round to the nearest hundredth. Well, hang in for a second. So if I round to the nearest hundredth, there's the hundredths place. I'm going to round at 7.14. But my math lab may also ask you, give the exact answer or calculate exactly or find the exact value of x or whatever. If it says exact, that little word exact, my pen is just killing me tonight, usually means you're going to have to express it as a fraction. So here, what this would be, 5 times 10 is 50 divided by 7. Remember, division and fractions are kind of interchangeable. So you can just write it as 50 over 7 and then reduce it from an improper fraction down to a mixed number. So how many times does 7 go into 50? 7 times. 7 times 7 is 49. So how many pieces are left over? 1. So 1/7. So 7 1/7 would be the exact answer. So let's say that you get 24 mpg, and you want to know how far can you drive on 516 gallons of gas? How about 516 gallons of gas? How about how far can you drive on 14 gallons of gas? Well, this is where when we deal with rates are still used in these proportions, but we have to remember, what does 24 mpg really stand for? 24, there you go, 24 miles over 1 gallon. Once we have it written out like that, it's a lot easier. In fact, rates are pretty simple to put in a proportion because the units are there. We have 24 miles over 1 gallon. On the other side of this, we better have miles on top and gallons on bottom. Those units better stay the same. So this is a rate, though. We're going to use our proportions with a rate. And that's a good question. I mean, the units are different. That's how you can tell it's a rate. So the units have to be in there when it's a rate. So the 14 gallons, 14 has to go with the gallons, has to go on bottom because gallons go with gallons. So now to find our miles, we cross, multiply, and divide. 24 times 14 is going to give us 336. Very good. Divided by 1, still 336. So let's say at 24 miles per gallon, how many gallons would it take? How many gallons to go 516 miles? In your notes, try to figure that one out for me quick. We'll talk about it in about 30 seconds. So the 24 miles per gallon means 24 miles over 1 gallon. What do we do with the 516? Top or bottom? It goes on top because it's miles. So what we're going to get on bottom is going to be gallons, because that's gallons on bottom. We cross multiply and divide. 1 times 516 divided by 24. 21.5 is perfect. Okay, what happens if our proportion isn't so clean cut like that? Well, if I'm trying to find A, let's say I have A over 4 and I'm trying to find A. I could find A here by doing the 4 times 9 divided by 12 would give me that A equals 3. But there is a longer process that is strictly cross-multiplying. What cross-multiplying does is the two cross products have to be the same. So here, one of the cross products is going to be the 4 times 9, which is what? 36. The other cross product, the other diagonal, is going to be A times 12, which is just 12A. Thank you, 12A, good. Those have to be equal to each other. 12A has to equal 36. Now we can solve for A by dividing by 12. Perfect. So A still equals 3. Now, a lot of people look at this and say, well, it's just easier to cross multiply and divide, not write out the equation. And you're right there. For the most part, it is easier. But what happens when you have a math teacher that's not so nice and does something like this to you? We can't just cross multiply and divide here because the missing piece isn't just x by itself in one spot. But we can cross multiply. I usually start out with the diagonal of both numbers just because it's easier for me. We have the 2 times 40, which is what? 80. Good. The other direction, we have the x minus 4 times 16. Well, to write out the equation here, I'm going to change the order. 16 times the x minus 4 equals 80. And now I can do 16 times x is 16x. And the 16 times negative 4 is negative 64. Yep. Equals 80. Then what? There you go. We add 64. 16x equals 144. And yes, we divide by 16. And you were absolutely correct. X equals 9. How would you solve one like this? There you go. So x times x is x squared. And 4 times 9 is 36. You had that absolutely right. So x squared equals 36. What would we have to do to that? The square root would be x. 6. You're missing something. Or negative 6. Because negative 6 squared would also be 36. Usually, if you just put the positive answer down, you're okay. My math lab, if it wanted both answers, would give you 2 blanks to put them in. Okay, I think you guys have had enough for the day. I know I am dragging. I'm sure I'm probably really enthralling speaker right now with the energy level I have. So there is a new quiz that is due for tomorrow, Friday, at 11:59 p.m. And a new homework that is due for next Tuesday. The homework says it's due today or the quiz? I'll fix that right now. I'll make sure I get it fixed within the next couple minutes here, so it's due tomorrow.